For decades, we've all looked at SHA-256, the algorithm that secures Bitcoin, as this perfect chaotic scrambler. But what if it's not? What if that's all wrong? Some absolutely groundbreaking research has found a hidden geometric structure inside what we always thought was just a black box. Today, we're going to explore how this one discovery could change everything we think we know about cryptography.
So here's how we're going to break this all down. First, we're going to bust the myth of the perfect scrambler. Then we'll uncover this hidden geometric map that's apparently been hiding inside SHA-256 all along. We'll look at the zero-score compass that researchers are using to navigate it, then tackle the tricky twin problem they're running into. And finally, we'll ask the big question: what does all this mean? Is SHA-256 broken, or is it just bent?
We have to start with this incredibly bold claim from the research. I mean, this isn't some small adjustment. This is a direct shot at a core concept that's propped up digital security for years. What these researchers are saying is that our entire mental model for how these hashes are supposed to work has been fundamentally wrong from the start.
To really get why that quote is so earth-shattering, we first need to talk about the way we've always thought about cryptographic hashes like SHA-256. Right, so the classic analogy here is a one-way function. You put your data in one end, and a completely unique, totally unpredictable hash comes out the other. Think of it like mixing paint. It's super easy to mix blue and yellow to get green, right? But it's pretty much impossible to take that green paint and perfectly separate it back into pure blue and pure yellow. That irreversibility is the whole point. It's the foundation of its security.
Now, this idea of a perfect one-way scrambler, it actually has a formal name in cryptography: the random oracle. It's this theoretical ideal, right? A function where the outputs are so random, so unpredictable, that there's absolutely no pattern, no structure, nothing to exploit. This is the bedrock of trust for basically everything, including Bitcoin.
Okay, but what if that black box isn't a chaotic paint mixer at all? What if, when we actually peek inside, we find something with intricate, predictable mechanics? What if it actually has a structure?
And this right here, this slide captures the huge shift in thinking. We're moving away from the random oracle, that idea of a chaotic blender, and toward a deterministic machine. So it's less like mixing paint and a whole lot more like a complex origami machine. It performs a very specific set of intricate, precise folds. The final shape is complicated, sure, but the process itself leaves behind these subtle, traceable creases.
And those creases? Well, that's what the researchers are calling recoverable geometric residues. You can think of them like fingerprints, or maybe even topological scars that get left inside the algorithm's state at every single step. They're faint for sure, but they carry information. They're little hints about the original data that got folded up in the first place.
So, okay, if these fingerprints exist, how in the world do you find them and follow them back to the source? This is where the theory starts to get really, really practical.
This is the million-dollar question, isn't it? Well, the research proposes that we don't have to just blindly reverse it. Instead, we can use something they call a geometry-only reverse probe to kind of listen for very specific signal buried deep inside all that cryptographic noise. And that signal comes from the Zero-Score Theorem. Now this is the mathematical smoking gun of this entire paper. It proves that if you test a guess against those geometric residues we were talking about, only the true original input will produce a perfect mismatch score of 0. Every single wrong guess will have a score that's higher than 0. Always.
Just think about that. In this unbelievably vast search space with trillions upon trillions of possibilities, the one correct path is cleanly and uniquely marked with a perfect 0. It's like having a mathematical compass that points directly and only to the right answer. It just stands right out from all the noise.
And the data backs this up beautifully. They ran trials with thousands of false guesses, and the true input word wasn't just, near the top. It ranked number 1 with a score of 0 every single time. This is what they call rank 1 stability, and it's the proof that this compass actually works.
So you might be thinking, okay, if we have this perfect compass that always points to the right answer, why isn't SHA-256 just completely broken? Why can't we just reverse any Bitcoin transaction we want? Well, it turns out there are two enormous hurdles. The first is what the researchers have dubbed the round 8 bottleneck. That geometric map we talked about is incredibly complex, and right around the 8th round, out of 64 in the whole algorithm, the difficulty of the search just explodes exponentially.
This graph from their research notebook shows you that explosion perfectly. See that orange line? That's the path multiplicity, and it just suddenly skyrockets. The number of possible paths you could take just goes through the roof, making it insanely difficult to keep following that zero-score signal through all the noise.
The second huge challenge is the existence of what they call tail twins.
These are basically false inputs. They're imposters that are so geometrically similar to the real one that they also generate very, very low mismatch scores. Now, they aren't zero, but they're close enough to be really confusing.
And this is really the heart of the problem. It's like you found a perfect DNA match at a crime scene, which is great, only to find out the suspect has an identical twin. How do you tell the imposter from the real deal? To solve this, the researchers are actually developing a residual taxonomy, a whole system just to classify these twins and tell them apart from the true original.
And this isn't just theory, you know. They are actively writing code to build this taxonomy, mapping out the geometry of these twins to find unique signatures, things like chirality, that can reliably separate the imposter from the real input. It's incredibly detailed work. So, with all of that on the table, let's be absolutely clear about what this discovery means for things like Bitcoin, and probably more importantly, what it doesn't mean. Okay. This research does not mean Bitcoin is broken. It does not mean SHA-256 is suddenly insecure. The researchers themselves say this loud and clear, that round-8 bottleneck and the whole twin problem are just immense computational hurdles. So no, this is not a practical attack.
What this is, though, is a monumental paradigm shift. It proves the hash landscape has structure. It's not some flat, featureless desert. And that means the problem of finding an input is no longer a blind lottery of just guess and hope. Instead, it's a guided search, a guess under tension.
And the final takeaway is this. The random oracle, that old idea of a perfect chaotic scrambler, is dead. It's been replaced by this powerful new concept of a universal read-only memory. A vast machine, yes, but one that is ultimately structured and navigable.
You know, this research really forces a profound shift in how we see things. If our most trusted algorithm isn't random at all, but is actually a vast, navigable machine, it just makes you wonder what other hidden mathematical landscapes are out there, hiding in plain sight, just waiting for us to find them.